Hello, Royals. Let's talk some more about completing the square. Let's say our directions are complete the square. Or we'll do a couple of examples today. Let's start with a monic example, which I sometimes skip in class because I don't know why it's so large there. Because I don't like teaching students how to deal with it. If there's not a coefficient out front, I think we should be able to deal with it anytime there is a coefficient out front. But remember to work with a goal in mind. Your goal is to get this function into the format a times x minus p all squared plus q, which means you want a perfect square monic trinomial. So this question, we're already set up to be a monic trinomial. Our only concern is to build these two terms into a perfect square. And I really like visualizing that with a sketch. I don't think you have to do it, but I think it's a great idea, especially when the culminating comes around and it's been months since you've completed the square. I should have probably just drawn this because I only have my x squared and x terms. This area of 6x has to be split evenly between there, which means I know the dimensions of this square. It's going to be x plus 3 by x plus 3. So to complete this square, I'm going to add 9. Now, the other thing I want to show you with this question is there is more than one way to complete the square. The way that I generally teach in class, I think, is the most reliable, and that involves you adding the number that would complete the square. Of course, I can't just add 9. I have to add 0. And then we've built a perfect square trinomial, so we can now factor that as a perfect square. Notice my sketch already tells me what that factorization is. I might want to start developing some shortcuts as well. Normally, I may have a multiplication here that would be required. Well, you know what? I won't do the shortcut here. It seems sort of silly for me to not do -1 or -9 plus 1 in this question, but maybe in a future question, it'll be a little bit harder to see that. So here we go. I've completed the square. I've changed this from standard form to vertex form. I can read off that the axis of symmetry is x equals -3. The optimal value is -8. The curve has been translated left 3, down 8. I could draw a sketch of it, all sorts of fun stuff. I guess my y-intercept should have been +1, but okay. So the other approach to completing the square that I want to show you is once we figure out that to complete the square, we would need to have a +9, some people go like this, and they say, well, I've already got +1, so I just want to upgrade that to a +9. So what have I done to change this one into a 9? Haven't I just added 8? Not everybody likes seeing this because it's not really explained how I've gone from what I've done to get from 1 to 9. Although I guess you could make the argument that I'm just rewriting 9 or 1. I'm decomposing 1 into 9 minus 8. I think a reader should be able to see that. And if we're working with purpose, they should understand why we did that as well. We did that because we wanted a +9 there. You could try that approach, or maybe that approach sounds more familiar to something that you were taught at another school. Right. Let's try another. Let's say we're asked to complete the square for g of x equals 2x squared plus 2x. Well, first thing that I want to mention about this example is I'm not so sure I would ask you to complete the square for this example. Okay. Because if I wasn't asked to complete the square, let's say instead the directions were find the optimal value for this. This is binomial. I know that I could get my x-intercepts by writing this in a factored form. That means that I have x-intercepts of 0 and -1. So I have an axis of symmetry halfway between those of 0 minus 1 divided by 2, which is going to be -1/2, and an optimal value of g of -1/2, which is going to be, I'm going to go into factored form here, I guess. 2 times -1/2 times -1/2 plus 1 is going to be -1 times 1/2, which is going to be -1/2. So I'm pretty sure I have my axis of symmetry and my optimal value. I think I'm ready to write g of x in vertex form with an a value of 2, a p value of -1/2, and a q value of -1/2. Sorry. But I was asked to complete the square, so I should complete the square. Now, working with my goal here, I'm trying to get a monic perfect square. and I don't have a monic term here. I don't have a coefficient of 1. So my first task here is to remove a factor of 2 from the first two terms. Notice there's no constant term here, so things actually look a little bit easier. Right. And now the question right here, this is actually a homework question. It looks simple, but because this isn't an even number, it's actually a little bit more complicated. I'll draw my sketch here. I have rectangular areas of x squared and x that split evenly. That means that each one of these is going to be half of x. So my square is x plus 1/2 by x plus 1/2. So to complete this square, I am adding the fraction 1/4. Make sure you're working with fractions. You're not decimals. Right. That subtraction of 1/4 happens inside the bracket that is being multiplied by 2. I may talk about some shortcuts in class if we want to try speeding this up. There's the square that has an area of x plus 1/2. But I'm not so sure. Like when I give you homework and you have 12 questions where you need to complete the square, I would understand why students are looking for shortcuts. But on a quiz or on a test, you're only going to be doing this like once or twice. So I'm not really sure you should be looking for faster ways of doing this. Okay, it's worth the time that it takes to show all of your steps. Notice these two agree with each other, but given the directions complete the square for, a student would not receive full marks for doing this process. Completing the square is something that you need to be able to do, and I'll tell you when you have to do it. It's also something you could choose to do in the future if you think you prefer the approach. So let's try one of our more difficult examples. Let's dig one up that has a fractional coefficient out front and on our b term. Let's complete the square for -2/3 x squared plus 8/9 x plus 1. I'm going to show you the efficient approach here for dealing with fractions, and I'm going to work by hand with my fractions. I think on the side, I want to show you what happens if you're not working efficiently, because it's a real mess. So reminding myself of my goal. Can I fit it in here? Almost. Yep. I want to have a perfect square trinomial on a positive 1x. So my first step is to remove a factor of -2/3. It feels like I am common factoring. Like that's the type of common factoring that the type of factoring that I'm doing. But I'm not sure that I would argue that -2/3 is a factor of 8/9. Okay. I can solve a simpler problem and remind myself that when I am factoring to find my quotient, it's as if I am dividing. I did 2 divided by 2 to give me positive 1x. So over here, or let's say off to the side, I want to perform 8/9 divided by -2/3, which is something I expect grade 11 students to be able to do by hand. It's something I expect grade 9 students to be able to do by hand. You'll get faster at working by hand by practicing working by hand. You probably have a calculator that can do this for you, but if you just keep reaching for it, you're never going to get faster or better. Now, I am going to make my numbers smaller before they get larger. I see a factor of 3 in the numerator and denominator. Let's divide those out, simplifying first. I see a factor of 2 in the numerator and denominator. Let's divide those out, simplifying first, giving me -4/3, which is in reduced form. Oh, I keep forgetting to mention this. A common mistake in formatting is students not writing the x here. To me, that suggests the student's trying to memorize a process and they don't understand that they've just removed a factor there. Right. Next goal is to make a perfect square out of those two terms. That's going to happen inside of my square brackets. -4/3 x. I like writing out all of this stuff because I know it has to be there. In fact, a couple of students have asked and then noticed that to complete the square, you're always adding first and then subtracting. If these two areas were positive, the product of two positives is going to be positive. If these two areas are negative, the product of two negatives is going to be positive. So here's my square over here. I have x squared. -4/3 x has to be split evenly, so that's going to be -2/3 x each. I suppose I could over here say I did -4/3 divided by 2. Now I did -4/3 divided by 2 in my head because I know that half of 4 of something is 2 of those things. That means that half of 4/3 is 2/3, or half of -4/3 is -2/3. This is what another time where reading this number properly in English is really valuable. If you're reading it as 4/3 divided by 2, you have to remember, do I divide the top or the bottom, or no? Yeah, then even doing -4/3 multiplied by 1/2, I don't think is the most efficient approach, because I will get students writing down -4/6, which isn't wrong, but it's not reduced either, and we always want to be reduced. There's my -2/3. Right. That means that my square is x minus 2/3 by x minus 2/3, and that this region right here is a square that is -2/3 by -2/3. 2/3 times 2/3 is 4/9. It's 2 times 2 over 3 times 3. I see they're all relatively prime, so it can't reduce. So I complete the square by adding 4/9. I balance that by subtracting 4/9 to make sure that I add nothing, so that I add 0. Sorry. It's a big difference between nothing and 0 in math. Okay, 0 is one number, right? There's not nothing there. There's something there. Let's factor this. Again, our factoring skills aren't really challenged here, because I can see on my sketch that this is a square that has dimensions x minus 2/3. I mean, I should double check maybe and make sure that when I do x times x, I get x squared. Minus 2/3 x minus 2/3 x would be minus 4/3 x, and -2/3 times -2/3 would be positive 4/9. There's those 3 terms being factored, compressed into a square of a binomial. So I still have the minus 4/9 to deal with. And then to attain my goal, I'm going to distribute through by this a value, giving me h of x equals -2/3 times x minus 2/3. It's sort of coincidental that those numbers are the same. And then over here, maybe off on the side, I'm doing -2/3 multiplied by -4/9. In this case, I see there's no simplification. There's no shared factor of 3 that's being divided. There's no shared factor of 2 that's being divided. So the best that I can do is write this as 8/27, positive 8/27, because the multiplication of 2 negatives will give me a positive. And this is where I always go back in time here and prepare my common denominator so that I don't need to write myself an entire other step to get my optimal value. Sorry. Let's see, 8/27 plus 27/27 is going to be 35/27. This is a course level example. Sketching this is also course level. We discussed this in class, that graphing this would be problematic, but drawing a sketch should not be. It's a parent quadratic that's been vertically reflected, vertically stretched by 2/3, translated right 2/3 and up 35/27. Now, I may have been, if I didn't look at standard form, I may be nervous about what the y-intercept is. I know my y-intercept from standard form, h of 0 is going to be 1. I can substitute in h of 0 here and still get 1. Try it out for yourself. But maybe I'm not actually even interested in the y-intercept. Maybe as far as a sketch goes, all I'm looking for is a curve, a labeled curve that's opening down, that has a vertex labeled at 2/3 comma 35/27. Okay. Now, the inefficiencies that I wanted to talk about happen when students don't reduce their fractions. So all the way back here for this number right here, if I had kept 8/9 multiplied by 3/2 and just gone negative, going to work for me. Prepare a pen ahead of time. Third time's charm. Okay, yeah, if I had just done 8/9 multiplied by -3/2 and gone -24/18, I mean, that's not wrong, but it's not reduced either, right? And then if I were to do, okay, what's -24/18 divided by 2 wholes, and get -24/18 multiplied by 1/2, I could have written down that's going to be -24 36ths right there. So each one of these is negative 2436, which means that this area right here, when I do negative 2436 squared, I mean, my goodness, I'm going to need to grab a calculator to do this. I don't have a calculator. Yeah, there's one. So if I'm still not seeing that this can be reduced and I do 24 squared, I get 576 and 36 squared over 1,296. I mean, this fraction should reduce down to 4/9, but I'm just making the question way harder by not simplifying first. There it is. I shouldn't need a calculator to do this. I might feel I need a calculator because I don't know how to do 20. Well, I should be able to do 24 times 24 off on the side as well. Make sure that you reduce as you go. You always want to keep things simplified. This is how we worked with fractions algebraically in grade 11 and how you should have been working with fractions by hand in grade 6, 7, 8, 9, and 10. Okay. It does take practice, though, so keep practicing completing the square.